All right. All right, so we are recording now. All right, so I actually wanted to make this a little bit of a hybrid presentation for the most part, given that I think some people, are only gonna take this in via video. So I want to just get a little point across real quick regarding the layout of the class and where we are in this class real quick. So we're coming to the end of the class. I am vigorously catching up on your grading. Again, it's COVID time. I've already spent an exorbitant amount of time in this class as it is, and even with all the time I've spent, I'm still behind. But right now, I have made the last recording as of Tuesday. Actually, yeah, I think Monday or Tuesday I made my very last recording, and so chapter 31 is done, and I am now focusing entirely on getting caught up with grading. But again, I have limited time, so I'm going to grade one major thing each day. So like, I'm going to do exam one day, chapter 21 homework, 22 homework, so on and so forth. I mean, we'll get all caught up. But one of the things that I want to point out real quick, and I'm going to go as quickly as I can, but I'm not going to. I just by definition I can't go overboard because I'm a person with limited time. I want to point something out in this class is, yes, this week we are in chapter 30 officially. Exactly 2 weeks from today is Thanksgiving. All right, and so that entire week, the entire week of Thanksgiving, we are officially off. All right, and so yes, we don't meet anyway, but there's really there's no new assigned stuff. But generally speaking, this week is a chapter 30 week, and next week is a chapter 31 week, and that's it anyway. So by the time Thanksgiving comes around, there will be no more chapters to study. All right, and so next Thursday, as you know, November 29th is exam is exam 3. But I want to point one other thing out real quick. Let me share my screen. I'm just going to share the top of my syllabus real fast with you. If you see on the upper right of my syllabus, we have a last day to drop. That's also next Thursday. And so, I usually the way things work out is they oftentimes are right aligned. The last day to drop is oftentimes aligned with exam 3. I don't have any control when exam 3 is. I don't have any control when the last day to drop is either. It's great when it is when the exam 3 is a couple days before the last day to drop. That way people can kind of assess where they are in the class. But you will have exams by the time next Thursday, the very day of exam 3 is also the last day to drop. So by the time you have that day arrive, you will have had exams 1 and 2 graded. I will try to have graded all the homework. You've already had about 3 labs graded. So I think at that point you'll have enough of statistical sampling of how are you doing in the class to make a decision if you actually want to drop the class or not. So again, I'm sorry I fell behind the grading, but right now I'm fully concentrated on grading. So again, it's just part of the whole COVID thing. There's only one of me. I don't have unlike other professors in other schools, I don't have a lab TA. I don't have anybody helping me out. There's no, I'm doing a lot of things heroically kind of on my own. So that's just the way it is, I guess. So anyway, just want to point that out.
Those efforts don't go unnoticed, and so thank you for that.
I appreciate that. It just seems like my wife kind of pointed out the other day. She goes, "You work so hard and yet you're still behind." I'm like, yes, that is true. So, but I'm going to get caught up. I certainly don't want to let you guys down. And anyway, in the class, so that's where we're heading. It's just we are heading toward the end of the class. So I have to look up when the actual final exam day is. But actually, I have leeway there. Normally you have an assigned exam time when things are normal and you have classrooms, and one of the things you have to deal with is logistics of the classrooms. When is this particular classroom available, so on and so forth, for an extended period of time. Usually exams are longer than, final exams are longer than usual. In our case, we don't have that situation. We basically meet in the virtual room. And so what I typically do is I push the exam out as far as I can in the final week. So weeks in this school, exam weeks always go Monday, Tuesday, Wednesday, Thursday. So we will have our final exam, which is not really a final exam, right? It's exam 4 over the modern physics concepts of relativity, quantum theory, atomic physics, nuclear physics. We'll have that exam on the last day of final. So it'll be on a Thursday, and I'll specify that. So, and then
that's scheduled for December the 10th, Thursday, December the 10th, right now.
Good. That's when it's going to be then. I don't know when the assigned time would be, but it doesn't, like I say, it really, for us, it doesn't matter, because I just have to get my grades in, my final grades in before a certain deadline. I usually am pretty fast at that. Believe it or not, this semester doesn't seem like I'm very fast at anything, but yes, I'm usually very fast. I'm one of the first professors to get their grades in, so I usually just get it done. And honestly, when I give a grade, when any professor gives a grade, it goes straight to your transcript, real time. I mean, when I give the grade, your transcript's automatically updated. And I think for people who are trying to get into medical school or pharmacy school or whatever it is you're trying to get into, it's very helpful that your professor is trying to be, considerate about your time as well. So I try to be very fast about that. And it's good to just have the class over too, All right, so that's that. So again, next Thursday. So just repeat. I'll just write it on the whiteboard just to be official about it. So exam 3 is on Thursday, November 19th. Last day to drop is Thursday, November 19th. Now I want to point out one more thing. This was told to the professors by the administration for us to tell you, the students, and that is, we do not drop you. Previous semesters, if you didn't show up for class, you had bad attendance, and you strung enough absences together, I literally will get a little button, a little stop sign button that pops up, and I just hit the button, and I'm required to do so. I mean, you're normally speaking, you're required to be here 15%, or you're required to attend the class 15% of the time. Everything's thrown asunder by COVID, and we're doing a much more of a we call non-synchronized teaching. Like, I give the videos and stuff, right? Well, with that said, you as the student are responsible for dropping yourself. You're responsible to know when this drop day is, and if it passes and you're still here, then you're here for the long term. So again, I'm not necessarily talking to you two guys, but I'm talking to anybody who listens to this video. All right, and so just keep that in mind, that professors at TCC, at least this semester, probably next semester, do not drop the student. Again, that we're told specifically, if you look at my syllabus, there is a specific clause that says that's in there, and that was told to me by the administration that I must put this in my syllabus, and so I followed and did exactly what they asked me to do, of course. So so that's just to let you know. So all right, let's get to the lab now. Sorry about the administration details here. All right, the lab. So the lab is geometrical optics. Again, geometrical optics is something we covered a few weeks ago. It's so geometrical optics is the topic of chapters 25 and 26. So if light, which is electromagnetic wave, of course, interacts with objects or holes, and a fancy word for hole would be an aperture, of a size much greater than the wavelength of the light, then the light acts like rays. Literally, hang on, let me text my wife real quick. All right, there you are. So we can literally model this process as a phenomena of like geometrical rays. Again, a ray in geometry is a directed line segment. All right. So again, it acts like rays, and in geometry, a ray is a directed line segment. So literally, we go from doing waves and electric fields and magnetic fields and all the like in what I call electromagnetic theory proper to really looking like we're doing ray geometry. So again, in geometry, a ray is a directed line segment. All right. So the term is really a true mathematical term. Okay, so when we go into geometrical optics, we have we call two laws of optics. All right, and so you imagine what happens. You imagine a ray of light traveling in some sort of material. We'll say the material on one side. This is what we call an interface. This is called the normal. Again, it is a perpendicular to a surface. All right, so a ray is traveling through medium one, and medium one has what's called this is an index of refraction. I'll talk about this a little bit more in a moment. Well, I'll just talk about it right now. Index of refraction simply says that, we know the speed of light. So light travels at speed c equals 299,792,458 meters per second in a vacuum. All right. If a medium has index of refraction n, say this. So in a vacuum, right? If a medium has an index of refraction n, then light travels slower. So if a medium has an index of refraction n, then light travels in that medium at speed V equals C over N. All right. So again, you know, this N is I'm going to say in here that I have one material on one side of the interface. We'll call it N1. On the lower side interface, I'll say that the material has index refraction N2. All right. So the light travels at a lower speed because it goes through an interface, and of course N is a number greater than 1, or well, greater or equal to 1. If it's 1, it's actually a vacuum. So N is unitless, greater or equal to 1, because C is the speed and V is the speed. N has to be unitless. All right. So for our purposes, we can think, for this lab, we can think of a given material as having some index of refraction. All right. And so we can imagine that, let's say, you know, you can assign, you know, for our purposes, we can think of it, you know, we can think of index of refraction as being a constant value. So for the purposes of this lab, we can think of the index of refraction as a constant value. Assigned to a material or characteristic of a material. So generally, you know, you might say, okay, well, what are some typical values? Well, N equals 1 for a vacuum. N is like 1.000293, which is about equal to 1.0 for air. And for this lab, we're going to take N for air to be 1.0. I mean, you know, again, it's not a vacuum, but it's really close to 1. You know, a good value for water, 1.33 for water. N is like 1.52 for glass. For diamonds, N is like what, 2.42 for diamonds, so on and so forth, right? So any given material has an empirically determined value of the index of refraction. So in that material, light travels through that material at a slower speed, given by the speed of light in a vacuum divided by the index of refraction. So light slows down. Now, index of refraction is more complicated than this, of course. We know that, I mean, in reality, the index of refraction actually depends on the electronic states of the atoms that compose the material. All right, and index of refraction. So the index of refraction depends on the quantum states of the atoms. Composing the material. And also the index of refraction is wavelength dependent. That's why we have dispersion. That's why we have rainbows. So this gives dispersion, also called dispersion. which gives rainbows. All right, and so, but for our purposes, it's just a number, and in the software, you say air, you get 1.33. You say air, you get 1.0. You say water, you get 1.33. You say glass, I think it's 1.50 or something. I mean, so we'll look at the software in a minute. All right, so now there are two we call laws of optics. All right, and so let's talk about those for a moment. We have what's called the law of reflection and the law of refraction. So law of reflection or Hero's law. Law of refraction or Snell's law. So Hero's law, again, this goes way back. These are Hero is one of the greatest scientists from antiquity. He's officially Hero of Alexandria. So he is somebody who was fortunate enough to see the Library of Alexandria before it was burned down. But he is one of the great. He was an inventor and a scientist, one of the great scientists from antiquity. And Hero's law is essentially says the following. Now we have an incident ray striking interface. We'll say this is an incident ray. What's going to happen? We're not going to worry about absorption. We're going to worry about that the ray is going to do the ray really can do one of three things. It can reflect, it can transmit, or it can absorb. Now we're not going to worry about absorption. So as far as reflection is concerned, and again, the normal is what's important here. So the angle with the normal, we'll call that theta sub I. Okay, and then the ray reflects, it's going to reflect at an angle theta sub R. Okay, this is the reflected ray. And then we have, let's kind of consider the N2 is greater than N1 for the moment. We know that what's going to happen is if N2 is greater than N1, the refracted ray will actually bend toward the normal. We'll actually have a refracted ray that comes toward the normal. It'll go at an angle theta sub T, T for transmitted. All right. And so this is the refracted ray. Refracted, the fract, and refracted means that it comes from the word like fracture, broken. So you imagine that the ray, if it wasn't for this interface, it would just continue straight. It looks like it's suddenly broken, like a broken pencil. So we talk about refracted, it means fract comes from broken. All right, looks like the ray is broken. All right, and so now law of reflection basically says that theta sub I is equal to theta sub R. The angle of incidence equals the angle of reflection. And the reflected ray is in the plane of incidence. Now, what's the plane of incidence? Plane of incidence is a plane, mathematically, that is formed by the incident ray and the normal. All right. So again, the plane of incidence, you imagine this, like say this whiteboard, for instance, right? I have a ray and I have the normal. Incident ray and the normal, if they're in the same plane, let's say the plane of whiteboard, then it defines this plane. All right. So the plane of incidence is the plane, mathematically, formed by the incident ray and the normal. So, this doesn't have to be like this, but but it is. That the reflected ray happens to lie in the same plane as the normal and the incident ray. All right. And so that's the law of reflection, otherwise called Hero's law. Then we have the law of refraction, otherwise called Snell's law, and that law says, well, you take the index of refraction of material 1, N1, times the sine of the angle of the incident angle, theta sub I, is going to equal the index of refraction of material 2, N2, times the sine of the transmitted angle. And again, the refracted ray lies in the plane of incidence. Refracted ray or transmitted ray. Transmitted ray in plane of incidence. A lot of people forget this last little part, but it's really important to know that it's in the plane of incidence as well. So again, these are the two governing, we call laws, I'll put in quotation marks, of optics. They are not laws of physics. Okay, the law of reflection and the law of refraction are not laws of physics. All right, and I'll explain that because number one, you can actually, in a most formal way, so I'm going to erase this. In a formal way, you can use Maxwell's equations to essentially match rays at an interface, and you get what we call Fresnel's equations. Fresnel's equations, you can derive the law of reflection, law of refraction from Fresnel's equations. So again, optics is, as we know, is not a separate field in and of itself. It is an aspect or a part of electromagnetic theory. All right. So optics is part of electromagnetic theory. And this theory is entirely described or entirely based on just 5 equations, all right? On the 4 Maxwell equations, and the electromagnetic force law. Not Snell's law and Hero's law. Okay, those are not 2 of the laws called out there, right? So it turns out you can match an electromagnetic wave at an interface and derive Fresnel's equations. Again, that same Fresnel, Augustin Fresnel. We talked about him earlier. He's one of our bonus questions. Same guy. Fresnel's equations, which give the law of reflection and the law of refraction. All right. One more thing. Okay, so again, that's the formal way of doing it with electromagnetic theory. We can also explain the law of reflection and law of refraction through Huygens wavelengths. and I showed you, I proved refraction to you in one of the videos. All right. So again, you can use Huygens construction, or you can use or you can model, or you can construct wavefronts. And use Huygens principle. Huygens actually, yes, his name ends with S. Huygens principle to derive the law of reflection and the law of refraction. So we have a couple of different ways of deriving the law of reflection and the law of refraction. So it is not a law of physics. Remember what a law of physics is? Law of physics is the behavior in the universe that is always true, but does not have a more fundamental cause or more primary cause. It is the primary cause. So if you tell me, for instance, if we have a why questions, and you say why is that, and I answer, oh, it's because of that, and then why is that, well, it's because of that. Eventually all of your why questions are going to lead to a law of physics. And if it's like, why is Gauss's law? The answer to that is I don't know. It just is. It is a fundamental truth of the universe. We don't know why. We have to find these laws of the universe. It's part of the fabric of the cosmos. We have to find these laws of the universe, and they are fundamental truths. All right. You cannot. So again, clearly, so Maxwell's equations are this way, and the electromagnetic force law is this way, as are Newton's 3 laws of motion, as are the law of universal gravitation, and so on and so forth. The law of reflection and the law of refraction are not that way. Because why? Because I have an answer to your question. If you say, why is the law of reflection, why is the law of refraction? I say, well, let me show you. Let me go to Maxwell's equations and give you electromagnetic wave, and let's match an interface, and I'll derive Fresnel's equations for you. Or, hey, let's make a Huygens construction like I did in class, and I'll show you, for instance, I will derive the law of reflection, the law of refraction. Given that I can do that, that means that these laws of optics are only laws of optics, laws in quotation marks, all right? So that's really more or less the main theory of optics I want to talk about. So what about this lab? Well, this lab, as I said earlier, you can think of again a ray striking interface. Here's our interface again. Here's our normal. And let's imagine I have a ray striking interface, and I'll say this is the incident ray. Here is theta sub I. And if I imagine here that, again, I have material N1, and on the other side of the interface, material N2. And let's again say that N2 is greater than N1. Well, again, no matter what, I'm going to have an angle. I'm going to a reflected ray at theta sub R, and of course, theta sub I is equal to theta sub R by the law of reflection. All right. Now, my refracted ray. Well, we'll find out if N2 is greater than N1. We'll find out that the ray is bent toward the normal. All right. So if N2 is greater than N1, the refracted ray is bent toward the normal. All right. That's typically how we'll think of things. But how? So this could be a situation like maybe this is air and N2 is water. Maybe N2 is glass. Again, I'm going from a lower index to a higher index. The ray will bend toward the normal. What if it's the other way around? What if it's N2 is less than N1? What if, on the other hand, what I actually have instead is that this is water and this is air. Let's say that N2 is less than N1. Well, in that case, if N2 is less than N1, I'm still going to have the reflected angle equal to the incident angle. But if N2 is less than N1, the refracted ray is bent away from the normal. All right, so it flares out. I say flares out, but it's bent away from the normal. All right, and so so if I'm coming out like this, maybe it's bent some, or that's not very good. Maybe it's bent out like this. Maybe that's my theta sub t. The picture's not very good, but again, you get the idea. Well, what you'll find out, and we're going to find out in this lab, is that I can look at successive values of theta sub I. And as I increase theta sub I, I'm going to notice that my theta sub t is going to get bigger and bigger. I mean, again, what is theta sub t? I mean, if I look at things here, I say, well, let's look at Snell's law. I have N1 sine of theta incident is N2 sine of theta transmitted. So let's see here. I divide both sides by N1. I have sine of theta incident is N2 over N1 sine of theta transmitted. Or actually, let's do it the other way around. Let me solve for theta transmitted. I think it'll look a little better here. So theta transmitted is going to be what? It's going to be N1 over N2, or the inverse sine of, okay, I have N1 over N2 times the sine of theta incident. Now, in this particular case, again, N2 is less than N1, so we're going to see here is that the transmitted angle is going to do what? As I increase theta sub I, that's going to have an effect of increasing theta sub t. Now, in this particular case, N1 is greater than N2, so what I'm going to end up doing is what I'm seeing here is that the greater I make theta sub I, the greater I make theta sub t. All right, and so theta sub I gets bigger. What I'm going to end up having is theta sub t is going to be progressively bigger until it gets to a special situation. At some point, there will be a critical angle of incidence such that my refracted ray is right along the surface. Okay, it's right along the surface. And so I'm going to have a very special incident angle such that I don't see a refracted ray at all. It is literally along the surface. All right. So what is that telling me? That tells me that if I go back to Snell's law, N1 sine theta initial is N2 sine theta incident, N2 sine theta transmitted. All right, well, I'm in a certain situation where I have a very special angle of incidence. I'll call it the critical angle. I'll put a little C here instead of I. It is a critical angle that does what? It gives me no refracted angle. Okay, I have 90 degrees right here. What is the sine of 90 degrees? 1. That means that, and for any angle greater than this critical angle, there will be no refracted ray whatsoever. It'll all be reflected. So for any theta sub I, so let me solve for this. So sine of 90 is 1. So what I get is I get N1 sine of the critical angle equals N2. I want to find the critical angle when all this happens. Well, I literally can just divide both sides. Here I have a sine of theta critical is N2 over N1. And of course, I think the inverse sine theta critical is the inverse sine of the ratio of these indices. And of course, N2 has got to be less than N1. Otherwise, I have an invalid argument for the sine function. The sine function, of course, the argument has to be less than or equal to 1. All right. So what this tells me is this gives me the critical angle. For any incident angle greater than the critical angle, all light, 100%, will be reflected. We call that total internal reflection. All right. And so we define this critical angle, or we calculate this critical angle. So the critical angle, again, sine of theta critical is theta critical is the inverse sine of N2 over N1. And of course, we must have that N1 is greater than N2. All right. So we must be going from water to air, or something that's going from a higher index to lower index. All right. Now, for any incident ray greater than a critical angle. So for any incident ray, where theta sub I, its incident angle, is greater than theta sub C, there will be no transmitted ray. All of the light, 100%, will be reflected. Now, why am I so stuck on this 100% stuff? Well, because this is one of those things in physics where you actually have perfection. You have literally 100% reflection. You don't get that anywhere else. If you go look in a mirror, even if it's the most efficient mirror as possible, what you're going to get is the power return of your reflection. It's not really going to be the light that's coming to the mirror. You get about 4% loss. You're going to get a power return of about 96%. There's always losses. Right? Except there is no loss here. This is one of those situations in physics where you literally have perfect reflection. All right. I mean, there's very few things like that. Like we've talked about a superconductor. Superconductors, you have zero resistance. You can take a superconductor and you can literally put as much current through it as you possibly can imagine. As long as you, I mean, the problem with superconductors, you have to keep it at very, very, very low temperatures. But you can run a current as much as you want. Don't worry about I squared R heating because you have no R. All right. I mean, why do you have a circuit breaker in your house? Because even any kind of a conductor, as good as it may be, is always going to have resistance, and you put enough current through it, you're going to fry. You're going to cause I squared R heating. You don't have that problem with superconductors. So it's some situations where you need to have a very large amount of power, like for instance, the quantum computer that Lockheed Martin and Google, there's 2 quantum computers in the world, one owned by Lockheed Martin, one's owned by Google. That's run on superconducting circuitry. I mean, essentially, it's in a very special place that's away from everything else, because you have to have that kind of computer processing. You're solving problems like, facial recognition at the airport. Somebody walks in the airport, and the idea is, why Lockheed's interested in is you scan the person's face, like, okay, every single person walking the airport, they get their face scanned, and then it goes through this whole internet search. Let's say I see Harmon. Okay, I see this guy in there, and okay, his name is Harmon Nelson. He is okay. He's associated with this. Okay, oh, he's a good guy. All right, no problem. I mean, but if you see somebody and all of a sudden you start seeing really bad stuff come up, then you You watch that person. Oh, we got a live one, right? And so the ability to process at that level takes a quantum computer. And so again, you have a tremendous amount of power do you need. And so this is why you have to have, you know, a situation where you have zero resistance. Perfect conductor, a superconductor, zero resistance, perfect reflection. All right. So that's what makes, so this whole, and so we call this is called total internal reflection. When I say the word total, I mean, it means just that, 100% reflection. Okay, we call that TIR oftentimes. Okay, fiber optics works this way. You know, the internet you get, you know, if you have a FiOS or something, literally you send signals all the way across the world, and you literally will have light or the signal having zero losses because it's constantly being totally internally reflected within the fiber. You know, the air on the outside has a lower index refraction than the very pure material in which the fiber is made out of. And so literally you have lossless transmission of signals. All right, and so fiber optics is in the fiberscope, the colonal fiberscope that doctor uses once a doctor wants to look inside your colon. Well, instead of, you know, you can actually have a little light at the end of a camera, and it's literally, you know, you go into the colon and the doctor can look around and see inside your colon, and that information is being transmitted back by fibers, optical fibers that are doing total internal reflection. All right, so this is a very important, you know, this lab, the concept of this lab is very important. So, all right, so let's talk about one more thing too. As far as the power, part of the lab, you're gonna see there's gonna be a certain percentage of reflected light. So we're gonna see, like, at some angles, you're gonna put a little probe that's on the lab. You say, okay, I have you know, a reflection happening, and I put this little probe and it says, oh, 2%. You know, 2% is getting reflected. What does that mean? Well, that means if you look at the total power, the light, this light, the power of the instant ray, you know, the power is going to be, there's going to be transmission plus reflection equals 1. That means that in this particular case, only 2% of the power is getting reflected, 98% is getting transmitted. As you'll notice that if I get the angle of incidence bigger and bigger, you'll notice we'll notice this goes up. And so what happens is less gets transmitted, more gets reflected, and then you get to the total internal reflection. And guess what? T becomes 0 and R becomes 100%. That's another way of saying it, that not only is there no transmitted wave, your reflection coefficient, your reflected power is 100%. All right. So again, you'll notice that when we have a little probe that kind of allows us to see the return on the reflected ray, and you'll notice that it goes to 100% and it stays at 100%. All right. So that's all the theory I want to talk about. So let's talk about the experiment. Experiment's pretty straightforward. So I've already fired it up. Let me find it. Here it is. All right. So let me share my screen. Any questions before we proceed?
None that I can think of.
Excellent. All right. So it's a relatively simple concept, but it's phenomenally important and it's fascinating as well. All right. Do you guys see the bending light interface?
Yes, I can.
Awesome. All right. So in this lab, you're going to want to click on Intro. There it is, and you'll get this this little layout here. And what you see here is, you know, you have an option of a ray or a wave. We want the ray because we're doing optics, and this is basically a laser pointer. And so what we want to do is want to, you know, there's a little picture on the bottom of page 1 that kind of says, okay, we want to make the incident material, the incident material to have a greater index of refraction than the material on the other side of the interface. And so we're going to set the first material to water. And you'll notice that the index of refraction goes to 1.33. And then we'll set the material on the other side of the interface to air. And notice that the index of refraction there and the indicator goes to 1.00. And then we're going to basically push the little button here, and that's going to give us an incident ray, a reflected ray, and a transmitted ray. All right. And let's see here. And he'd like, oh, that's another thing too. We can grab a protractor off the toolbox and very nicely lay it right on the interface. So we can make a nice angle here. Yeah, I think that's all right. And then what we can do is we can have the incident ray, we can set it, and I think he wants initially at 30 degrees. So let's set it at 30 degrees. And you'll notice here that, as I said, the angle of incidence is equal to the angle of, the angle of reflection is equal to the angle of incidence. You notice that the reflected ray is also at 30 degrees. And then the refracted ray, it's looking at about 40 degrees, right? And so the refracted ray looks like 40 degrees. So as I said, I would expect the refracted ray to be larger because, or the transmitted to be larger because, again, we're going from a higher index material to a lower index material. And so when that happens, the transmitted ray bows outward, it goes away, bends away from the normal. All right. And so again, that's corroborating what I said. All right, I'm on page 2, top of page 2. And so we set this up. Now we want to gradually increase the angle of incidence to about 40 degrees. And we'll read off. So I'm gonna make this go to about 40 degrees. We'll get a reading. There you are. And so if you look at that, that's let's see, that's about 50. Let's see, it's not quite 40. Yeah. So let's see here. That's 40 degrees. That's not. I'm sorry. I'm at 35 degrees, aren't I? Yeah. 50. I don't think I have this thing set well enough. Well, maybe I do. Something's not quite right here. Oh, that's it. This is wait, this is 40. There you are. All right, and so, all right, that's lined up now. Lining up like at 40 degrees like that. Again, we see that the reflected ray is at 40 degrees. Transmitted ray is just shy of 60. I think it's 58 roughly. So it's just shy of 60 degrees. The transmitted ray. All right. So I'd write on there, I'd write what the angle of reflection is and the angle of refraction. And that's all there is to do in part 2. Part 3, top of page 3. Keep increasing the angle of incidence till the angle of refraction is close to 90 degrees as you can get it. If you increase the angle of incidence further, then the reflected ray will disappear. So the angle when this happens is called a critical angle, and we want to find a critical angle for water. All right. So again, we have water on the incidence side of the interface, and we have air on the other side. So for water, so we increase this angle, keep increasing it. As I said, you notice that the refracted angle is closer and closer to 90 degrees. Again, this thing is a little bit touchy. So get it right there. Looks like it's about right there. So I look at that, and that's about 49 or 50 degrees. Again, that's a critical angle. Notice that there is no longer a transmitted ray. Transmitted ray disappeared. what you have is a reflected ray. You have purely a reflected ray, and that is it. You don't have any transmitted ray. All right, and so if you look at, there's a little indicator here, and again, this is something we're going to do later on in the lab, but it kind of give you an idea. We have an intensity indicator. If you look at it right now, we say, oh, it's 4.66%, not much at all. But as I increase, I look at the reflection light back, and now I'm at 10.2%. Go a little further, and now I'm getting a reflection of about 28.6% ish. Continue going further. Now the ray disappeared. And look at that, 100%. And for any large array, I'm just going to continue getting 100%. So again, 100% of the energy is being reflected back. None of it goes into the air. All right. So anyway, so I got about 49 degrees ish for the critical angle of water. So they want you to do critical angle for. I'll do step 4 as well, and then I'll let you do the mystery A, and mystery B. So again, all you do is you say, okay, well, let's see here. I'm going to do the critical angle for what now? It's the next one. Step number 4 is glass. So let's set the first material to glass, and let's try to see if we can find out where the transmitted ray disappears. And there it is. All right. So it disappears again. It's very touchy here. Right there, about 90 degrees, and it's disappearing at around, it's like about 41 or 42 degrees. And you can kind of play with it as well. And then you can, what it wants you to do in step 5 is it wants you to use mystery material A. And notice that there is no there is no index of refraction given for that. It's gonna be left to you to determine it. And mystery material B, but you'll just go and set them like that, and kind of go and do the exact same thing I did, and look at where the transmitted ray disappears. All right. So again, step 4, and step 4 is the glass. Step 5 is mystery A and mystery B. So you'll set it again. You'll set the material on the top part of the interface, top of the interface to mystery A. And then on the top of the interface, then you'll do exactly what I did before to try to determine what is the critical angle, and then set it to mystery B and determine what the critical angle is again. All right, so I'll let that be done by the student. Now, step 6 is you're going to make a determination of what the angle of a refractive index is for particular material. So for water, Dr. Edmonds kind of did the work for you here. So we saw for water that the critical angle, again, I'm looking at the table on the bottom of page 3, step 6. The critical angle for water we determined to be 49 degrees. So again, if you take so let me kind of explain this this table here briefly. So back to my whiteboard. All this table is doing is the critical angle calculation I did a minute ago, right? And so this table is saying, okay, well, we know that, again, we're looking at a situation where, you've already determined what the critical angle is, right? We know that, let's say, for instance, this is water. So N1 is 1.33. And we know at the other side of the interface, this is air. And we know that N2 is 1.0. So we're going to use Snell's law. And he's basically walking you through Snell's law in this table without really telling you that. So Snell's law is, again, what? It's N1 sine theta 1, or theta incident, is N2 sine theta transmitted. Now, we're particularly looking for the critical angle. So we let the incident angle be that very special angle, theta critical, where theta t is 90 degrees. We also know that N2 is 1. All right, well, let me just keep the initial step and then I'll make the changes. So again, this is theta initial, or I keep saying initial, theta incident. Here's theta transmitted. So again, what this really comes down to is N1 sine theta critical is N2 is just air. That's 1. All right. And we have sine of 90 degrees, which is also 1. So what we really have in this special case is that N1 sine theta critical is just 1. Or sine theta critical is 1 over N1. All right. And so what you're looking for, so what he's walking you through, if you look at the first column, he's saying, okay, well, you have the critical angle, you found that to be 49 degrees. You take the sine of it, you take 1 over the sine. Well, that's so what you're actually doing, I apologize, we got one more step here. You're solving for n. We're gonna cross multiply. So you're saying that N1 is 1 over sine of theta critical. All right. So if you look at that table in step 6, he says, I want you to determine theta critical. Okay, well, we got theta critical. There it is. Now take the sine of theta critical. All right, sine of theta critical. Now give me 1 divided by that. Okay, 1 divided by sine of theta critical. What does that give you? That gives you the index or fraction of whatever this material, in this case, water. All right, so he's walking you through this algebra as you read the table from left to right. All right, so let me go back to sharing my screen. That's all he's doing there without really telling you he's doing that. He's just walking you through the algebra. So again, looking at the, you guys see the software again?
Yes, we can.
Awesome.
So on that first one, will you show the calculation how he did that?
I will. Yeah. All right.
I mean, it's just like,
yeah, let me do that. That's a good idea. I'll go through the first 2 rows and then you guys can do the mystery. All right. So
thank you.
Yep. All right. So you see the math. So, oh, here goes my pen. All right. So so we found the critical angle for water. Found that to be, so this is for water. Found a critical angle, and we found it to be 49 degrees from the software. Okay, so you say, okay, well, what is the sine of 49 degrees? Sine of 49 degrees is 0.755. So you would write that in the first row. You write that under the sine of C column, the second column. Then your next column is 1 over sine of critical, or 1 over the sine of 49 degrees, or 1 over 0.755. And what you get then is you get 1.33. And that is N1 for air. If you do, let's say, the second row is glass. So glass, we found the critical angle to be 41 degrees, designed it. All right, and then same process. We're going to go and fill out the table from left to right. So the sine of theta critical is the sine of 41 degrees. And I get 0.656 for that. The next column of the table, again, I'm looking at the second row, is 1 over sine of theta critical, which is 1 over 0.656. And that gives me 1.52, which is the typical index of refraction of glass. And refraction of glass is 1.52. So you're going to determine for the last two rows, you're going to determine a critical angle for mystery A and for mystery B. And you'll go through the same process. You'll find the sine of the critical angle, 1 divided by the sine, and you'll get whatever the indices of refraction are for mystery A and mystery B. All right. Any questions?
I can't think of anything.
Excellent.
You are still wanting the refractive index for mystery A and B, even though it's blacked out, right?
Yeah, write that on the side. I'm not really sure why. I think he chose a color that came out a little dark. So yeah, we do. Yeah. So please write the indices of refraction that's supposed to go in that column. Just put them to the side. So please, all students watching this video, please pay attention to that statement. Write the indices of refraction for mystery A and mystery B on the side of those darkened column or those darkened cells. Okay, I'm on page 4 of the lab on task B. All right, so task B is really more of the same, but now we're going to use that intensity indicator that kind of broke out to you guys earlier than I guess the lab wanted me to. So let's go back to the software. Share screen. All right. So we want you to again have the material, the top material be water. And I'm setting it up like the top of page 4. And the bottom of the lower part of the interface to be air. We want that intensity indicator. And we're going to set it up so that our first angle is 10 degrees. And he kind of gives you the answer there for the first one. You kind of see what the intensity is. We're not going to get the same answer, but so that's maybe roughly 10 degrees. We put the intensity meter at the right in the path. Oh,
Isn't it the other thing?
I got it backwards. I haven't eaten yet. All right. Here we go. Trying to get to like 2.19. I think he had it. All right, there you are. So that's his setup. You see that in the picture, and he writes it in for you. So you look at the angle of incidence, you set it for, again, we're filling out this table on the bottom right of page 4. You look at the angle of incidence, you see 10 degrees. You write the 2.19. Again, that's 2.19%. That means that out of all the intensity, which is basically power divided by area, and what's power? That's energy delivered per unit time. It's basically an energy measurement, more or less. But out of the intensity of the incident beam, there is a reflected ray and a transmitted ray. So transmitted ray is getting like 98% of all the intensity. The reflected ray is getting like 2% or 2.19%. So again, there's not much return off of this reflection. There's a reflection, but the intensity is only 2.19% of what the incident ray is. But we notice something, you know, like we go to 20%. 20%. I put the intensity, I put the meter back, and I get 2.87%. So it looks like it's getting bigger and bigger. I'll do 30 degrees. (4.71%). So again, the greater I make the angle of incidence, the greater the return intensity, reflected intensity. Again, it's a relatively small number. We're saying that 95% of the intensity is transmitted into the air, and only about a little less than 5% is reflected back into the water. And you know, you just keep on going. I mean, I'll let you do some of these, but let's take it to, you know, again, there's a 35 and a 40. I'm gonna go straight to 45. All right, we'll go straight to 45. Again, I want you guys to do some of this, so I'll leave those measurements for you to do. 45 degrees incident angle. 22.1%. Great. So we're really starting to see something now, right? And so now we're seeing, okay, now it's 78% gets of the light gets transmitted from the water into the air, and 22% gets reflected back into the water. All right. But then we get to that point where, if you remember the critical angle for water, we saw that was 49 degrees. So watch what happens to the percentage return very quickly. Yeah, we're at 45 degrees right now. It's kind of ramp up in a hurry. Let me kind of get there. Look at it. Ramps up way up to 49% really quickly. Right? It went from 22% to 49%, and just about another degree or so, we're at 100%. So now, very, very quickly, it spikes up, it ramps up from a low percentage return to now everything is returned. All the intensity is in the reflected ray, and there is no transmitted ray. Again, the intensity indicator is stating that the reflected ray is getting 100% of the intensity of the incident ray. And if you were to do any other, I mean, again, Dr. Edmonds wants you to do 55 degrees, 60 degrees, 70 degrees, so on and so forth, right? We see this happening right around. We know that 49 degrees is that critical angle for water. Okay, we know that. But any other angle, any other greater angle, again, we want you guys to increment to all the various angles. But any other angle, you're going to find out that you pick is 100%. Again, it is entirely the light. The light is entirely reflected back into the material, back into the water, for any angle greater than the critical angle. And again, so you're noticing total internal reflection right at the point of the critical angle and beyond. So the critical angle from 49 degrees all the way out to whatever, all the way to 90 degrees if you wish, is all, or 89 degrees. 90 degrees is probably going to give you a weird result, but all the way out to 89 whatever degrees. It's all the light is going to be totally internally reflected, TIR. Okay. So there's a question at the bottom of page 4. It says, using the data in the table, suggest the value for the critical angle of water and explain why you have chosen that angle. So why would I choose that angle? Why would I, from the table, why would I choose, let's say 49 or 50? Well, the table gives you 50 degrees. So I will find out that I'm at 100% at 50 degrees. Can somebody explain to me why I would consider that a critical angle? There's two things you can say here. Anybody want to take a shot at it?
Well, I mean, I'm happy to do that. I would just say because the refraction rate has gone to zero. Your refraction rate, you have no refraction rate.
Well, I wouldn't say rate, I would say intensity percentage.
Excuse me, right?
Oh, I'm sorry, refraction. Sorry, refraction. There's no I'm sorry, I know what you're saying. There's no refracted ray. Is that you meant ray?
Yes.
Yes, you're right. You're absolutely right. Yes, refracted ray. You're absolutely right. The refracted ray goes to zero, but there's one other indicator, and that is the intensity of the reflected ray is 100%. Two indicators here, right at that very special angle. Your refracted ray totally disappears, just like you said, Harmon. And the other indicator is that the intensity of the reflected ray is 100%. Those are the two indicators that tell you that is the critical angle, and that at this point and beyond any other higher critical angle, any incident angle greater than the critical angle, you'll have total internal reflection. So again, your data is telling you that, I mean, it's really 49 degrees. We'll say because of the granularity of the data being taken here, we'll say 50 degrees for this data set is the critical angle, and we see that, and so those are the indicators that is where total internal reflection occurs. That's how I'd answer that question. And remember, when you answer that question, two things should be mentioned. Number one, the transmitted ray disappears. There's only a reflected ray. And number two, the intensity of the return of the reflected ray goes to 100%. Those are the two things you can notice. All right. Now I'm on the last page. The last page is kind of a, I guess, freestyle. It's kind of like play with the tools and kind of tell me something that you see. So I'll just kind of go to them briefly. And, you know, anybody watching this video, tell me two or three things that you see in the tools. So we'll go to the prisms. So let me back up. Any other questions before I go to the last page?
I can't think of any. It's been pretty straightforward.
Very good. Awesome. That is good to hear. All right. So when I hit the back button, looks like I go back to the beginning. All right. So I'm at the fire up the software yet again. So give me a moment. And I just played around for a few minutes in these, and he just wants you to kind of look at some of the other interesting tools. So there's prisms. Prisms, when this thing finally loads, prisms actually look at the dispersion of light. So it's, what causes a rainbow, for instance. So you go to the prisms, click on that, and what you see is you see different media that you can be in. Like right now you're in air, you can be inside of water, you can be inside of glass, right? So you can play with that, whatever medium that you're in. And then you can pick a prism, like you could pick the famous triangular prism. Set a prism out here, and you can actually rotate a prism. This little thing on the bottom here is like a little thing that causes rotation. You can click on that, and I'll just open up the laser. And one of the things that I found a little bit more interesting is, we see the laser option, but here I like to see kind of more of a, I would say more of a beam of light. And now notice that, let's see, I think, yeah, actually this is white light. Actually, this is red light. So the first indication, this is an actual laser. Here it's a laser beam. Here, the last option on the right is white light. So laser beam is only going to be monochromatic. You're only ever going to see red light coming out of a laser. Okay, and you can select the laser color as you wish as well. You can play with that and play with the You can play with the wavelength of whatever the laser light is, or you can, and of course that would also apply to this more distributed light, laser light, or you could go to white light. White light's where you see your rainbow. All right, and so you can pick different, you can also pick this different, you can make a prism made out of glass. You can make a prism made out of, I guess water. Just different materials for the prism. You can make, instead of having this triangular prism, you might pick something maybe like a sphere. See what it does. Or maybe like this thing looks kind of like a lens or so. See what that does. You have different things you can play with. I mean, so I guess play with this a little bit and kind of, write down 2 or 3 things, maybe 4 things that you found interesting with this prisms. All right. The idea is it does dispersion, and so the triangle is really helpful for that, because the triangle essentially makes the light come in at an angle and leave at an angle. And so you literally will have different, you have a theta sub I that's not 90 degrees, it's not normal, and you have a varying theta sub t, like in the dispersion problem, like we talked about in the exam review. All right. All right, so that's prisms. And then we go to the very bottom of this lab, and that would be the more tools. And I gotta go through this long loading process. So I mean, again, say 3 or 4 things that you noticed or you found that was neat about, or maybe some things that you think you can do with the prisms tool. Now, as far as more tools are concerned, I didn't really see a lot there, but here's more tools. That's the very, very last part of the lab. And I'll be easy grading. I mean, don't blow it off. I'll give you full points. So if you say, you pick out some, interesting things about these things. So I'm going to click on more tools. More tools. Again, if we go, here I have air and I have glass. I have, let's say, glass the inner side. That's perfectly fine. I have a protractor. I have an intensity meter. I have a couple other things like if I click on here, I actually have the ability. So yes, I have the ability to determine the intensity of return light, just like I did before, or I can actually do the intensity of the transmitted light. All right, so 90.8%, then I should have what? They should all add up about 9.2% near side, right? They should add up to 100%. I also have the ability to figure out the speed of light. I can measure that. So I can put it here. Here we go. Speed of light is c, 1.00 c. I mean, it's in air, it's basically c. But if I go to inside the water, oh, I'm sorry, inside the glass, I should see that it is, so it's about 2/3 c. So again, you can kind of see what the speed of light is in a material. And if I decide to make this material water instead, for instance, I would, I think I can do this. There is 0.75 C. That's a well-known fraction for water. I might be able to really quickly determine what the index of refraction of the mystery material are. So I can say, oh, mystery A, what's it going to be? Well, I can really quickly determine, oh, okay, V equals C over N, huh? All right, so one divided by that, well, that is C over N, and so I can basically flip N upside down and figure out what that is, right? So I can quickly determine what the mystery material is by just knowing the definition of, how the speed of light in the material is related to the index of refraction. V equals c divided by n. So these are all various things I can play with. I can also make a wave. So I can also look at wave phenomena. All right, so those are all the various things that I saw playing around. So again, this is and there might be other things that you see. And maybe I can play with right now I have a red wave, maybe I have a green wave, blue wave, so on and so forth, right? So I have different and I can also employ my intensity meters still. So I can still say, oh, it's 28.79%. Okay, this is like 71%. So again, I can do a lot of those same things. So again, I can generate something that's much more wave-like, or I can look at something that is, again, a ray. So again, these are all the various tools. I say just play around with it and kind of tell me 3 or 4 things you found to be instructive in this as well. So again, for the final page, for prisms, again, give me 3 or 4 things you saw that are instructive, and why are they instructive? What do you think? Why do you think they might be important to you, or what might they tell you? And then in the more tools, same thing. 3 or 4 things you saw that you felt that were of importance or relevance, and maybe why you think they're relevant. The tool to measure the speed of light, that's very relevant. You can use that to measure the index of refraction, for instance, or so you can think of things like that as well. So anyway, that's kind of a free for all. Again, I want you to write something on that last page, but I'm not going to be majorly critical on the last page. I'm hoping to give everybody points on the last page. So again, my hope is to give you points. So, all right. Any other questions? That's the lab.
Dr. Callahan, I don't have any questions for that.
Okay.
But I do, after we finish recording, I have an Mcat question. I was wondering if you would not mind clearing up for me.
Sure. In fact, I promised DJ a long time ago I was going to give him the 1,001
It's okay.
MCAT
Second
question.
semester is the charm.
Yes, so it will happen. I owe 2 other students from physics. I just got busy, but you will get those questions. I promise you.
Hopefully before the MCAT.
Yes. When are you taking the MCAT?
In May.
Oh yeah. You'll get it before the end of the semester.
Okay.
I think things are more normalized now that I'm done with these videos.
Yeah.
Yeah, I didn't know if you wanted to stop recording and I could ask you the question, or if you wanted that to be a part of the. I don't care either way.
I think let's let the recording be for just the lab, so I can stop recording now. So, and DJ can hang around, or all right. Let me. Oh, you know what? If I stop recording, I do so by ending the session. So let me end this session. That way I stop. Well, then I have to wait for the session to record. Do you mind making a part of the recording? Is it?
I'm fine with that.
Okay, that's cool.
So everybody know that going here forward, this has nothing to do with our lab.
Yes. You can leave.
Okay, so in our MCAT book, it has to do with constant force, and there were some things that, because it's been a while since I've taken physics 1, that seemed to be a bit confusing, and I'm happy to read it to you.
Okay.
It just says students tend to have a common misconception regarding force and acceleration. Make sure that you understand the following. It says first that a constant force will not cause an object to accelerate faster and faster. It will cause a constant, non-changing acceleration. So that's just saying that if you are applying a force, a certain amount of force, a constant force, acceleration is not going to happen. So don't assume that. Is that right?
You could, so for instance, if you have a boulder, and you can apply all the force that you want, it's not going to accelerate.
Yeah.
All right. So the bolt. So again, just because you apply a force doesn't necessarily mean the boulder's going to accelerate. Now, on the other hand, you could apply a force to something you can move, and you would cause an acceleration. A constant force would cause an acceleration. But then again, what's important about Newton's second law, you have to keep in mind here is, I mean, again, what is Newton's second law? Let's kind of go back to that briefly. So Newton's second law is saying that the sum of all forces on an object, again, it's a system concept. The sum of all forces on an object is the mass times acceleration. All right.
Right.
So for instance, if I have an object, there's other forces on it. Maybe the normal force, maybe its weight, maybe drag force from the air resistance, and maybe the force that you're pushing, maybe a thrust force. Maybe you're pushing some force. So yeah, you might apply a constant force, but then again, the faster this object goes, the drag force goes as v squared, right? So it goes as 1/2 c rho a v squared. And so, kind of like if you put your hand outside the window, your hand hits hit by a big force. So again, this force goes up as well. So there's other forces. The idea with Newton's second law is that you may apply a constant force if the situation is very, very simplified. Like I don't have to worry about drag, and these two forces here are perpendicular. Then that acceleration would be constant. However, there's other forces involved in the problem. Like for instance, this force here, the air resistance increases. I mean, in fact, if you're dropping something, let's say I drop say a raindrop, for instance, right? A raindrop, what's it going to do? Well, it's always going to have mg, but as the velocity gets bigger and bigger, the drag force gets to a point where eventually it gets what's called terminal velocity. It gets to a point where finally d and mg are the same. Then what happens is it's just going to fall at a constant speed. And we're very fortunate that happens. Otherwise, raindrops would kill us.
Right.
And so that's so again, you might apply a constant force, but it really also depends what other forces. Because remember, it is the left side of Newton's second law is a vector sum of forces. I think that's what your statement is saying.
Yeah, it does. But then it goes on to say,
Okay.
Only a changing force can cause a changing acceleration. So I understand that.
Yes.
It said, that being said, a constant force can cause an object to move faster and faster, in which case the displacement is changing non-linearly.
Yes,
the velocity is changing linearly, and the acceleration is not changing at all. And I got completely confused with that.
Yeah, so that's so it's kind of, let's look at free fall, for instance, right? So if I look at free fall, so it's we'll turn off air resistance and everything. So free fall says that, okay, you have an object where this is free fall is probably one of the best ways to have a constant acceleration, right? Because you have the acceleration of gravity. You have an object that's going to, let's say, it's going to feel gravity, accelerate to gravity. And so what are your kinematic equations again? Well, I have, my acceleration is just negative g, all right? And then I have, let's say, v equals v naught minus gt. All right. So the velocity, well, that's what this is a constant. So let's say, for instance, if you drop the object from rest v naught 0, and this is a nice linear function. This is basically what you're seeing here is that your velocity, it's say negative, or let's just say let's use upside down coordinates. Let's let y positive be upside down. That way I can actually make things a little easier. I can imagine that the acceleration, the velocity, and the position are all going in a positive direction. So when you look at this, you say, okay, well, this is just, this is like an algebra 1 thing. Let's say at time t equals 0, I have some sort of b naught, and this is b versus time. And then what I'm going to have is it's going to go linearly, and this is going to be a slope, and the slope is going to be what? It's going to be g. So you have a linear equation. Now, what's another kinematic equation? Well, I have y minus y naught is B naught T plus 1/2 GT squared. I mean, I can get from one to the other by doing, you know, for instance, by doing integral calculus. I can integrate the velocity and get the position, for instance, if you're familiar with calculus. But you get this as well, and I derived this in physics 1 as well. I derived this, of course, without using calculus. What does this look like? Well, now, so let's just kind of write this a little bit differently. I'll put the y naught on the other side. All right. So now, what does this look like now? Well, if I drew a displacement curve, again, time is actually never negative. So again, keep that in mind here. So I'll do a displacement curve here. Well, it says, okay, well, my position, I'm just doing one dimension, is starting at y naught. So that would, in this case, that would be a height above the ground.
Mhm.
And then what's happening is, well, if, let's say B naught T, that's, you know, that's maybe I say that it's initially at rest, that goes to 0. And what I have here is a parabola. So I have a parabola. Right, that's just basically saying that actually, yeah, it's basically saying that I'm going further and further away from my starting point. So again, I made everything positive, so maybe it looks a little bit weird, but this parabola is going to be basically y equals some constant times t squared. So the position is parabolic, the velocity is linear, the acceleration is a constant. I mean, you graph the acceleration, for instance, in time, it's just constant, g. And so what that's telling you, that statement is telling you is essentially what the kinematic equations for constant acceleration tell you.
So the graph on the wall is going to be the displacement.
That's the displacement, yep.
Okay, that makes sense then.
Yes, so I probably could better say that, yeah, if you want displacement, then what I can write is this instead. And that way I can actually make it come from 0. So what this is now is y minus y naught. That's your displacement. That y is your position. Y minus y naught is your displacement. And then it's going to look like this. Some parabola. Or
Okay.
You get the idea. It's supposed to always be going up, but there's your parabola. So yeah, so the position is the displacement is a parabolic curve in time. Again, this is your time axis. Your velocity is linear, your acceleration is constant.
Okay. And the other thing it just said is it says a related misconception is that a constant force applied to an object will cause it to travel at a constant velocity. And it said this is absolutely not true. A constant net force will always cause a constant acceleration and therefore a changing velocity.
Right. Constant net force.
Yes.
Will give you a constant acceleration.
Okay.
And one of the things about a constant acceleration, again, remember the kinematic equations, if you want it, what's their official name? The official name is kinematic equations for constant acceleration. So if I was teaching this right now in chapter 2, whatever, I'll just put A there. That's their official name. Oops, kinematic equations.
Okay.
All right, so that is, so again, in order to be able to have these equations, you have to make the assumption of constant acceleration. And I make that assumption in, say, chapter 2 and chapter 3 before we talk about Newton's laws. All right, and so Newton's laws, so again, you start off doing physics 1 you start with physics 1 having no idea as to why things work. And that's what Galileo was, Galileo he didn't understand Newton, he didn't understand laws of physics. In fact, laws of physics were actually given to the world. That very concept was given to the world by Sir Isaac Newton. So he was the first human being on this, whoever lived on this planet, to understand the concept of laws of physics. And so he was able to explain what Galileo observed by applying, the the laws of motion, particularly Newton's second law. And of course, what makes Newton so amazing is that he had other scientists get excited by and wonder if maybe laws like this might be true for other areas of physics. Like might electricity have laws, or magnetism, or we didn't really, at the time we had no idea it was electromagnetic theory. Or how about heating or the thermal sciences? Might they have laws? Yes, they do. All of physics, all the areas of physics have laws, but the very concept, and I always tell people that Isaac Newton really has affected every human being who's ever lived since his time, because the fact you have technology is because people looked for laws of physics. Isaac Newton was one mind in a thousand years maybe to actually conceived of this. In fact, Newton his physical intuition was so incredible that there's a bridge that still exists in Cambridge today that Newton built, and he built it without nails. He had such an incredible understanding of the forces and stresses and strains of the material. He did not even need nails. One of the things he was amazing at, not only was he a mathematical genius, but he was able to build things with his hands. And, he was a master crafter. I mean, he was able to, and so because he understood, his physical intuition was so incredible, he understood forces so deeply. And so his insight was able to, and plus his mathematical genius, who put those beautiful things together, and he was able to conceive the laws of physics or laws of motion.
Okay. Well, that was helpful. It was confusing the way that they worded this, and I wanted to get some clarification on that.
Okay. Yeah, absolutely. You can ask me anytime. Would you, I guess, like your friend DJ, would you also like to have my Mcat Solutions?
Oh yeah, that would be wonderful.
It's called the 1001 Mcat problems. I'm a type A personality, and so I had to solve every single one of the 1001, of course. So you see these yellow.
You might have to wait 2 semesters for his answers.
No.
Just kidding.
No, I'll send him an email.
So did DJ. He's actually sent me a couple of emails.
It's okay.
No, I'll get those out, and I owe 2 people from Physics 1. This COVID thing is just throwing me asunder, or throwing me into craziness. But yeah, it's a little yellow book called 1001 Mcat problems, and I'm always happy to send them to my future medical doctors.
Yeah, I'm currently working through our Physics 1, and some of it's coming back, and it makes all sense in the world. And there were just a couple of things that's just throwing me for a loop. And I thought, well, you've got enough on your plate, but I thought while I had a captive audience, I'd get you to answer that question for me if you didn't mind. So thank you.
And also, to point out, in my YouTube site, I have all of my videos. So I've done videos
Right.
for every single chapter in the book. Well, I'm saying the first 31 chapters is actually, I think, a chapter 32 that we will not get to. I mean, basically, my videos are done. I much as I enjoy doing them, I got to do grading. So
Right, exactly.
that's not as much fun.
Well, thank you, Dr. O'Callaghan, for everything.
Absolutely, you betcha. Yeah. You guys, any more questions? Or
DJ, do you have any?
No, I think I'm good.
all right.
All right, thank y'all.
You will get those MCAT problems.
We'll
All right,
see.
very
We'll
good.
see.
All right.
Thank you.
Good one.
Bye.
Bye.